claus process. So claus process is a method of like removing sulfur from your petroleum component. So like in this claus process, what happens, the flue gas that comes out of my petroleum refinery from the top of my like atmospheric distillation column, it might contain significant amounts of H2S. So that H2S, you cannot allow it to go into the atmosphere. So you want to pretty much recover the sulfur. So claus process actually enables us to recover the sulfur by doing H2S oxidation. So H2S oxidation is a very simple process where like H2S, after getting oxidized, is going to give you like 1 mole of sulfur and 1 mole of H2O. So this process can happen in 2 stages. H2S first getting oxidized, converting itself into SO2, which is sulfur dioxide, plus 1 mole of H2O, and then 2 moles of H2S again reacting with that SO2 will give us 3 moles of sulfur plus 2 moles of H2O. So this reaction is exothermic in nature, and like reaction temperature and all. So that thing we had already discussed in our previous classes. So I'm not repeating the same thing again. So like here this what should I call it, this claus process will work out like if your system is containing let's say in the range of between, like at least it should contain uh, like it performs will be better if the percentage of H2S present in your flue gases is on the higher side, but it can also perform up to 5 percentage like by volume of your H2S concentration. But the higher the H2S percentage present, the better its performance would be. So the heat is recovered from the reaction gases, because as I have told you, this oxidation process is a exothermic reaction, and you cannot allow the heat to leave the system. You have to properly utilize it, then only your energy economy would be good. So that is why the heat after the reaction has to be like recovered. So heat recovered from the reaction gases in the waste heat boiler by generating high pressure steam. So the reaction gas leaving the waste heat boiler are then passed to a condenser, where cooling will take place up to, let's say, 150 to 190 degrees centigrade, and the condensation to elemental sulfur will take place. So the gases containing the unconverted sulfur will be again passed through the reactor containing a bed of bauxite catalyst. Finally the waste gas is going to be like oxidized. So the last traces of H2S and elemental sulfur, you can actually take it out, or you can also like vent it out from the, like vent it out to the atmosphere by your stack. So after the sulfur recovery, that elemental sulfur, you, I have already told you, you can also utilize it for other purposes like rubber vulcanization process. So total sulfur recovery using the subsequent claus traces ranges between 94 to 96 percentage, which is very good. The complete conversion of H2S to SO2 to your elemental sulfur is not like possible due to your thermodynamic chemical equilibrium of claus reaction. The selective oxidation of H2S to sulfur can be thermodynamically complete by reaction, that is H2S plus half O2 is getting converted into 1 mole of sulfur plus 1 mole of H2O. The series of proprietary catalyst like used for this direct oxidation of H2S to elemental sulfur are used, so like they do not disclose the composition of that catalyst. So because if you want to let's say the companies actually keep it a trade secret, so they do not disclose what type of catalyst that they are using. But obviously the catalyst must have a very high activity, or else like you cannot directly convert your H2S into your elemental sulfur. So that has been mentioned here. So I'll just show you one video on a sulfur recovery using claus process. So claus process, there's a similar type of process with a little bit of modification. So modified claus process we will discuss with this current video, and then we'll further discuss about merox oxidation process. So let me just share the video on claus process. Please let me know if you can hear the audio.
Now, most sulfur plants are based on the Claus process, developed by Carl Friedrich Claus in 1883. He discovered that the H2S reacted with air over a catalyst directly to form sulfur in water. The Claus process is highly exothermic with low efficiencies. Reaction control is difficult, and there's a high risk of overheating the reactor. So, enter the modified Claus process. This includes a highly exothermic thermal combustion reaction, followed by a moderately exothermic catalyst reactor section. And there's various configurations of this. They're a function of acid-gas feed compositions, minimum recovery efficiency, and maximum throughput. Also, the available utilities will depend on what kind of setup you need. So this is...
So one thing, let me just take you back to the original reaction. So one of the problem with this original claus process is that because of this very high exothermic reaction, there is a chance that overheating can take place within the reactor. So that is why nowadays you want to first convert your H2S into SO2, although which is a highly exothermic reaction, but the following step where your SO2 again is going to be utilized to convert your like H2S into sulfur vapor. So that process is a becomes, what should I call it, as a endothermic process. So it actually absorbs heat. So because of this combination of these two process, the overall reaction where your H2S gets converted into my like elemental sulfur by oxidation process, it becomes a moderately exothermic, because one part actually involves a highly exothermic process, the other part involves the endothermic process. So combine both things together, what it happens, it becomes a moderately exothermic process, unlike our like initial claus process, which was like very exothermic, and chances of reactor overheating is always there. So that is why this modified claus process is pretty much
setup
preferred.
you need. So this is a comparison, kind of basic flow chart between the Claus process and the modified Claus process. You can see with the original Claus, it's just one vessel. The furnace is actually within the same converter vessel there, but it's just that one thermal reaction going on. And then we see with the modified Claus process, we have the reaction furnace where the thermal reaction takes place, but then we have at least two more catalytic stages after, where the catalytic reaction takes place. And another sort of flow diagram here, we can see our feed streams going into the sulfur recovery unit include the gas sweetening unit, that's the amine unit, and then the sour water stripping unit if we're dealing with refineries. And then most SRUs today now use a tail gas cleanup as well to get the efficiency that much higher, hopefully up into the 99 plus range. And then we have incineration of our sulfur products that are turned into SO2 and vented out the stack. And then of course our product, our liquid sulfur, coming out the rundowns of our condensers. And that's degassed in degassing pits and then cooled and stored. Now we have a graph showing the temperature versus the conversion efficiency for the modified Claus process. And we can see here that for the highest recovery efficiencies, the Claus reaction is favored with a decreasing temperature. So what is recovery efficiency? It is the amount of H2S that's converted to sulfur vapor and subsequently recovered in the condensers as a liquid. So it's our recovery conversion, or our conversion efficiency, minus our sulfur vapor and any entrained liquid sulfur. Now, a 2-converter Claus plant should achieve at least 96% recovery efficiency. And then if you add another converter for a 3-stage, we should achieve 98 at least. Now we'll talk about the main potential losses to recovery efficiency. So we have catalyst deactivation, and that can be thermal, mechanical, or chemical. It can be from soot or fouling. It could be from sulfation, or you could have poisoning from VTEX breaking through into your converter. Also, off-ratio control is a big one. It has to do with the tail gas analyzer and air demand analyzer, which we'll get to. Excessive converter dew point margins. We want to maintain a nice little 10 degrees centigrade margin above the dew point temperature in converters 2, 3, or 4. Converter 1 will run hotter so that we can promote hydrolysis of COS and CS2. Which brings us to the next potential loss. If we have poor hydrolysis, that's a major contributor to losses. Then a poor operation of the demister pad will create sulfur fog, and this is also a big contributor to losses to our efficiency. And we also want to keep that final condenser outlet temperature to about 125 degrees Celsius. And anything higher, and you will notice losses due to vapor carryover. Excessive turndown is also a major one, especially nowadays. We're seeing more of this. The sulfur plant doesn't like to run when the feeds are turned way down or we have poor quality feed streams. It has a hard time running way below design capacity. And then our day-to-day operational upsets, which can really cause any of the above losses to happen. So some configurations, we have straight through, we have the split flow, and then we have other things like sulfur recycle and direct oxidation. And these all depend on the amount of H2S in the feed stream. A split flow process may be preferred over a straight through one if the H2S concentration is less than 50%. And this is where 1/3 of the acid gas is burned in the furnace, and then the other 2/3 will bypass it. So with that split flow design, that 1/3 going through the furnace is actually completely oxidized into SO2. And then that sets us up with the nice 2-to-1 H2S to SO2 ratio for the first converter. And that's key. So these all depend on, well, these are so we can achieve the proper reaction furnace temperature and then still get our 2-to-1 ratio. And it's all dependent on the acid gas quality. And these are some flow diagrams of those different variations. So we have the straight through, it's pretty simple, basic. And then we see in the split flow there, we have the bypass, where 2/3 of it is going and meeting up before the first converter. Then we have our sulfur recycle, which is exactly that. The tail gas, or a portion of the tail gas, keeps getting recycled to try to improve that efficiency. And that would be like a high turn down scenario. And same with direct oxidation. There's not even a furnace. It's just going right to the first reactor. Here's a conventional layout of an SRU, just straight through process here. We have our air and our feed acid gas going in. Then we have our waste heat boiler attached to the back of the RF. Our first condenser, then we have reheating and converting stages, which each follow a condenser. This is a 3-stage plant. And then we have a coalescer at the end, and then it's going to the tail gas treating unit. So this page is some general guidelines for achieving a strong performance from your SRU. So maintaining the correct process chemistry, which is that 2-to-1 H2S to SO2 ratio, this is perhaps the most critical one. Then we also want good process control. And that includes the upstream units like the amine and the SWS unit. And then directly in the SRU, we need our instrumentation to be calibrated. We need everything to be controlled how we want it. And then we also need to optimize our process parameters. And mainly that includes temperature. We want to make sure our reheaters are all achieving the right temperature for our converter inlets. We want to make sure our condensers are cool enough to condense all the sulfur that we can and minimize vapor carryover. Then lastly, we need a knowledgeable team of operators, maintenance, instrumentation, and management. They're all equally important in this, ensuring the performance of the SRU is good. So we'll talk a little bit more about this H2S to SO2 ratio. We want to ensure that this ratio is achieved at each catalytic stage. And to do this, we have a ratio controller, which controls the main combustion airflow based on the acid gas flow rate. So that's our bulk tuning. And then we have some finer tuning where the tail gas analyzer calculates the air demand signal, or ADA. And this regulates the trim airflow to the furnace. Now that finer tuning uses a air demand analyzer, and that formula is for its signal. So it's based off the tail gas analyzer, or the tail gas ratio. So if you look at the formula, if we plug in a perfect ratio of 2 to 1, that's 2 H2S to 1 SO2, that gives us 0. So the perfect air demand signal is 0.0. Okay, so this page, we have the conversion efficiency versus the air demand signal. So the key takeaway from this graph is that anytime the air demand signal goes outside plus or minus 0.5%, there will be an immediate loss in recovery efficiency. And it doesn't take much to get outside that range, so we need really smooth process control, and we hope our feed streams are consistent. Another takeaway is that the recovery loss gets a lot worse when the air demand goes negative. And to achieve a negative air demand, that occurs when the ratio gets too high.
So this is a very short video on this claus process. So if you want
most sulfur plants are based.
So actually, if you want to know more about the claus plant, you have to go through this particular video on claus converters. But here I just wanted you to discuss and understand about what are the parameters that can affect the performance of your claus plant, as well as different types of configuration of your claus plant. So if I ask you in the examination, explain what is the explain what is the different variation of your claus plants, I think just by because I have not mentioned this thing in my video, like in my PPT, but since I have shown you this particular video, and the link is also shared with you on the this thing on the bottom of this this PPT, so that you can also refer back to it. So other than that, this particular problem, like questions I might ask, that what is the necessity of controlling this H2S to SO2 ratio in this claus process, what is we are going to achieve through it, maybe a little bit of information about the claus process chemistry, like by optimizing what are the parameters we need to look at, what are the consideration we have to make in order to operate this claus process, and definitely the difference between modified claus process and the normal claus process can also be asked in the examination. So this video is like 100% one question is definitely going to come from this video. So maybe I have not mentioned the details in the PPT itself, but this particular video that I have shown you is very important with respect to your final FAT examination, because this question is not coming in your CAT 2 examination, but this type of question, like at least one small question definitely will come from this unit, that is from your the video that I have showed you. Okay, so like try to go through this video if you find time, and or else like one or two, like from here the questions that I can ask may contain around 3 to 4 marks. So 3 to 4 marks you won't be able to answer because the information that given in this video are not included in my PPT. Okay, so let me just go back to the process of sweetening process. So maybe another process, actually I would talk a little bit about after I cover this merox oxidation process, this amine treatment process, that this particular video also talked about. So that process also I'll be talking after we cover the merox plant. So let me just go back to the PPT itself. So I guess the difference between clause process, modified clause process, different configuration of the clause process, you have now have the knowledge about it. So let us just talk a little bit more about different other types of sweetening process. Sweetening process means obviously we are taking out sulfur from my petroleum products. So sweetening processes like we have to remove alkyl or aromatic mercaptan, important sulfur compound distributed in petroleum products can cause foul odor, oxidation problem, and obviously other than that it can also be considered as a catalyst poison. Like later on if it gets oxidized, then obviously it can lead to acid rain, and if formation of H2SO4 takes place obviously within the system itself, that may also have a detrimental effect. So mercaptan can also cause oxidation, determination, as well as inhibit the performance of the various additives. These additives are like octane boosters like TEL, and TEL means tetraethyl lead, and antioxidants in the finished product. So its removal is pretty much essential. So for mercaptan removal process, pretty much merox plant is pretty much used. That is why we call it as the merox process. That means mercaptan oxidation process. So mercaptan can be removed by two ways. One is this caustic scrubbing. The second one is this merox extraction. So conversion of mercaptans to, sorry, one second, make a mistake. Just like conversion of mercaptans to disulfide occur. Like disulfide include doctor sweeteners or sodium plumbite, merox sweetening, as well as copper chloride sweetening, acid treating, clay treating, or other like treatment may also you can go through in order to remove mercaptan from your petroleum products. Yes, so for this, like your doctor's solution treatment, so this is one of the like very useful chemical in order if you want to remove some mercaptans from your petroleum products. So, for example, you take the feed to be your cracked or straight run naphtha that is coming either from your cracking unit or from your distillation column. So, distillation column naphthas may content up to 0.04 percentage of naphtha. So in order to remove that, we will be using sodium plumbite, which is none other than Na2PbO3. So in the sodium doctor solution active reagents, sodium plumbite is present in the form like in a solution of caustic soda, which is none other than NaOH only. So your doctor solution reacts with the mercaptans, it leads to formation of lead mercaptide. So this is the like that is where my lead is actually coming up, and doctor solution, when your mercaptan will come in contact with the doctor solution, it will get converted into lead mercaptide. The sulfur reacts and leads, just a moment. So the sulfur reacts and leads mercaptan and gives this disulfide and lead sulfide. So now once this lead sulfide is produced, so you can now again regenerate. Hello, hello. So please do not turn on your microphone. So lead sulfide, now once we have converted, reacted your doctor solution with your mercaptans in presence of your caustic soda, that is NaOH, it has been converted into lead mercaptide. So now this lead mercaptide will react with sulfur to form give you disulfide as well as lead sulfide. So now you need to regenerate your lead sulfide, because you have to regenerate again your sodium plumbite, because like until and unless your the main agent or the main reactant is being regenerated in the process, so the process never becomes a very cost effective process. So this lead sulfide will be again regenerated using air plus your NaOH solution back to your sodium plumbite. So sodium plumbite basically consisting of your sodium, lead and oxygen, so it will get converted into sodium plumbite. The disadvantages of this particular process is that it is difficult in controlling polysulfide formation, so you won't be able to control polysulfide formation, and because of this treatment process, your octane number as well as color stability of your final product also deteriorates significantly. So that is what one of the negative aspects of this doctor's treating process for removal of sulfur from your petroleum products. So coming on to this one of the main sulfur treatment, that is my merox oxidation, or we can call it also mercaptan oxidation. So merox oxidation was initially introduced in the refining or petroleum refinery more than 40 years back. So the merox process became one of the UOPs, means Honeywell's one of the most successful process with more than 1,700 units licensed, because this merox treatment was developed by Honeywell first. So like whoever plant that will install this type of merox unit will have to give some royalty, or like it has to be licensed under Honeywell UFP. So even as the processing objective change to meet the impending sulfur demand content, sulfur content regulation, the merox process has been one of the key refining technologies with more than 300 merox plant licensed since 1990s. So it's a little bit old data. So merox process are characterized by catalytic oxidation of mercaptans. Your mercaptan will get converted into disulfide in an alkaline basic environment. Then what will happen, this RSH, which is none other than my mercaptan, getting oxidized, it is forming disulfide like RSSR plus water will be produced. In a liquid extraction merox process, the mercaptan in lighter feeds such as gases like C3, C4 or LPG and naphtha are extracted with a caustic solution. First of all, the mercaptans that might be present in your lighter gases such as your flue gases, maybe like C3 or propane based feedstock or butane based feedstock, or maybe combination of this both, which is like LPG is none other than combination of propane and butane only plus naphtha. So first of all, your like those petroleum fraction will be first treated with your caustic solution. So after naphtha extracted with a caustic solution, which is regenerated by oxidation with air in the presence of merox catalyst, the resultant disulfide are separated and the caustic is again reused for the extraction purpose. So first of all, caustic treatment will be done to extract the mercaptan, then you do the oxidation part. So once the oxidation process has happened, then obviously you will be forming this disulfide. So after you separate the disulfide, then you have to regenerate your caustic, because that caustic might contain like traces amount of sulfur, so that caustic needs to be regenerated, and after that it can be reutilized for your extraction purpose again. So like it involves two processes. First of all, involving my like caustic soda, it will be like basic atmosphere, you have to take out your mercaptan, then you oxidize it, form disulfide, separate the disulfide, and then you have to regenerate the caustic soda again for reutilization. So coming on to this slide, so this slide is actually talking about different types of application. So starting from gas phase, LPG, pentane, elasan naphtha, condensate, FCC naphtha, because like after cracking cracker naphtha also, other than that, the lighter product that comes out of your atmospheric distillation unit, that also you can process it. Obviously kerosene and jet fuel, because the purification requirement for those type of products are very high. So kerosene, jet fuel will also be treated with naphtha, and distillates up to 350 centigrade boiling point, you can be treated using this type of merox treatment. Sulfur content of the extracted extracted hydrocarbon is reduced. Heavier hydrocarbon fractions such as naphtha, kerosene, jet fuel, and diesel contains types of mercaptan which cannot be readily extracted from the hydrocarbon. In a fixed bed sweetening merox process, the mercaptan oxidation reaction takes place in the presence of air and merox catalyst. The mercaptan are converted to disulfide, and which remain in the sweetened hydrocarbon product. Overall, the sulfur content, the mercaptan sweetened in a fixed bed merox catalyst, have replaced the older liquid catalyst sweetening units. The merox process application for various types of hydrocarbons, so like what type of hydrocarbon your merox process can handle, so that has been depicted using this particular diagram. So you can also have a look into it. Because of its effectiveness, now it has replaced the older liquid based like sweetening process. So like this is talking about this liquid extraction part. Just a moment. Okay, so let me just go through this particular. Just a moment. Okay, so let me just go through with this slide, which is none other than explaining the process itself. So maximum removal of mercaptan is achieved in a single vertical extraction column using proprietary high velocity and high efficiency jet deck extraction trace. So proprietary means like you cannot, like the details of this type of units are not going to be discussed, like not going to be discussed in open literature, so you won't be able to find these details. So you see that naphtha feedstock flowing through the extractor column is counter currently extractant with a circulating caustic solution. So the first stage of treatment with the caustic solution, so naphtha feedstock flowing through the extractor is counter currently extracted with a circulating caustic solution. Depending on the feedstock properties, the required product specification, as many as 6 or more stages of extraction are incorporated into the merox extraction column design. It ensures maximum desulfurization with a minimum caustic circulation rate, reduces the capital cost compared to other processes that can achieve a single stage extraction per a contacting vessel. So they are saying that the purpose of using this multiple stages of extraction is that they want to use minimum amount of caustic but achieve maximum amount of desulfurization, because you are using the caustic in order to extract the sulfur from the feedstock. So like why we are using it for multiple times, because you don't want to use too much amount of caustic. So then if you are using too much amount of caustic, then regeneration will also incur a lot of cost. So that is why you are passing it through a like 6 or more stages of extraction. So it ensures the maximum desulfurization with a minimum caustic circulation rate, reduces the capital cost compared to other processes that can only achieve a single stage extraction per contacting vessel. If hydrogen sulfide present like if hydrogen sulfide is present in the field, the extractor column is preceded by a pre-caustic wash for H2S removal. So they are saying if you have a let's say certain amounts of H2S that is present in your, because your merox process is dedicated towards extracting like mercaptan, so that is SH, RSH. But if let's say some free hydrogen sulfide is present in your feed, so like you cannot just directly send your feed to your extraction column. So prior to that, you need to have a caustic pre-wash. So caustic pre-wash will take care of this hydrogen sulfide. So extractor column is preceded by a caustic pre-wash for H2S removal, removal of H2S prior to mercaptan extraction process provides a more efficient separation or operation, removing the H2S. The circulating mercaptan extraction process is not contaminated, which allows more efficient uses and minimizes the disposal or of the recirculating caustic. So removing the H2S, like by removing the H2S, the circulating mercaptan extraction caustic is not contaminated, which allows for more efficient use and minimizes the disposal. So they are saying that if the H2S is present in my solution, so it can actually contaminate my like caustic that is present in my extractor column. So that is why we have to go for a, let's say, a pre-caustic wash. So once we have done the pre-caustic wash, so all the H2S will be mostly removed, so the remaining feed will should not contain any H2S, and then you can actually send it to this mercaptan extraction process, where by using a very limited amount of caustic solution, we can actually extract a lot of mercaptans, that is RSH, and the regeneration or the disposal requirement will also not be there. So yeah, yeah, just a minute. Yeah, so see, this is the this is my this merox extraction process. So feed, if it contains certain amounts of H2S product, it has to be passed through that, and that is why this caustic pre-wash is done. Then it is moving into my extractor column, like multiple stages will be there. Then your extractor column is the bottom part, which is the mercaptide rich with caustic after the extraction process has done. Then you are adding low pressure jet into it, you are heating it up, then you are mixing air into it. So the purpose of mixing air is definitely to oxidize it. So in this part, your like mercaptide rich caustic will be oxidized. So once you have oxidized it, now you need to separate your disulfide. So this separation part will happen. So disulfide separator will be working here, then the spent air will be there, and the remaining part you can actually, from the bottom of this disulfide separator, you can again, which is my regenerated caustic only, because this mercaptide rich caustic we have sent to oxidizer. So after the oxidation process, disulfide we have been able to produce. So disulfide, after the separation has been done, so disulfide has been separated here. The bottom part, which is none other than my caustic, which we have regenerated using oxidation and this separation process, you can again send it back to your regenerator section. And the bottom, the top part of your extraction, that which may also contain a little bit of sulfurous compound, that is why it is sent to another caustic settler, and then it has to be further treated in a sand filter, and then you have your treated product. So that is my entire extraction process that is associated with my merox treatment. So simple thing, because we are let's say we are considering that your feed is having certain amounts of H2S. So if H2S is not present, so caustic pre-wash will not be required. So if H2S is present, that is why we are using this caustic pre-wash. Then we have this multiple stage extractor. So more than 6 stages will be there. So from the bottom, mercaptide rich caustic is like being extracted. Then it is getting heated up using low pressure steam. Then after, in this oxidation column, after getting mixed with air. So the purpose of air is to definitely provide oxygen, so it is getting oxidized. After oxidation process, we pretty much know after oxidation your mercaptide will become disulfide. So disulfide needs to be separated. So this is my disulfide separation plant. The remaining air will be like taken off from this separator, and from one side your disulfide oil you can take it out, and from the bottom of this separator you have your regenerated catalyst that you can again send it back to your extractor for again extracting sulfur from your feed. And the top part of your extractor column will go into your caustic settler, and then followed by a sand filter treatment, and then you will have your treated products. So these are the, in a nutshell, that is all about your merox extraction process. So the basic merox process we have already talked about here, so there is not much discussion that is left. So I guess in the next class we would be able to complete this merox treatment process. And then one of the most important thing that why from a refinery point of view, why we want to purify, or let's say we are so much obsessed with this desulfurization process, because I guess you people have already heard about the Euro 3, Euro 4 standard, BS1, BS2 standard. I guess you people have already heard about it. Now, do you know based on what criteria these BS standards are being made? Obviously, in order to match your BS6 or BS 4 standard, obviously you need to control your sulfur content as well as your part like nitrogen oxide and particulate matter content also needs to be under certain value. Then only your quality of your petroleum or diesel can match this type of BS standard. So those things we'll be talking about in the next class. So with that, let me just conclude today's class. So I guess with like I do not have in this slide currently the information about the your sulfur limitation, but you can pretty much understand initially our sulfur requirement or sulfur threshold limit in our BS2 standard was approximately 500 ppm. Now compared to that, your Euro 3 and Euro 4, you can see that the difference is way too much, almost like 10 times. Euro 4 and the BS2 standard has a sulfur limitation difference up to 10 times. Now with this BS3 standard, like BS4 and BS6 standard, we are almost at par with like Euro standards. Now the diesel that our Indian refineries are going to produce, like it is no way that is inferior to any sort of like any sort of foreign petroleum refinery, whether it's a US based refinery or whether it's a UK based refinery. So I guess this information is available. So you see now with this latest standard, your BS4 standard, we have just fixed it as 50 ppm, which is almost at par with my BS4 standard. Now with BS6 standard for gasoline I'm talking about, only 10 ppm. So now you see our like controlling, limiting the final sulfur present in my final petroleum products is so important in order to increase the value of that particular what should I call it, that particular petroleum product, that we are so much obsessed with this desulfurization process. That's why we are talking so much about, first of all we are talking about amine treatment, we are talking about merox oxidation, we are talking about this claus process. Why we are so much obsessed about this let's say sulfur percentage of sulfur present in my petroleum products, now you would be able to understand. Because now we want to match our quality of your petroleum product that is coming out of Indian refinery at par with any world standard. So now we are almost, BS4 itself is almost at par with your Euro 4 standard, and BS6 has even gone a step further, almost like 1/5 of the BS like Euro 4 standard. So you can pretty much understand the importance of desulfurization in any petroleum refinery. So we'll be talking about this in the next class. I just wanted to give you the idea about it, because we are talking a lot about desulfurization, but we are not talking about other treatments, like why we are not too much concerned about our like nitrogen removal. But you will see that here in BS6 and BS4 standard, we are also focusing on other aspects other than this particulate matter, like small like PM particles, like particulate matter limit also they have limited to be, it should be less than like 4.5 mg per kilometer. If your car runs for 1 kilometer, it should not emit particulate matter that is more than 4.5 mg, so which is a very high quality petroleum product. And they have also limited the nitrogen oxide limit up to like 60 mg. So you can pretty much understand the focus that has been given to your like petroleum refinery in order for you to like purify your petroleum products even more, because you want to match the global standard, or else like whenever we are emitting too much of nitrogenous compound as well as sulfurous compound, it has a lot of like environmental detrimental effects to the environment. So that also we want to limit to the best of our ability. So that is why we are being very much focused on this standard or all of these aspects. So we'll be talking about this in the next class. So with this, let me just conclude today's class. I'm just posting the poll question in general post section. Just answer to get your attendance. Thank you all for attending today's class.
Sir, sir,
Yeah. Yeah.
sir, last class you told like who wanted to present their TA one, sir, and then you told.
Yeah, but it is like, were you present in that class? You're not present, right?
Yes, sir, I was present, sir, in the class. I told, sir. Sir, I told, sir.